Hello and welcome to week 3 of the virtual learning, the online learning of the Higher Chemistry Nature's Chemistry unit. As you will be aware, we have been working on topic 1, which is an introduction to organic chemistry, covering systematic carbon chemistry, oxidation of alcohols and esters, which is what we're going to look at this week. So like I mentioned, this is week 3. Just before we get started on esters and take a look at what we're going to be learning this week, a wee suggestion for week 4. My current plan is that we are going to move on to the final topic of the higher course, which is it's a big moment. And that's going to be looking at chemistry of cooking and cosmetic chemistry. We're probably going to start with looking at the chemistry of flavour. So just some ideas if your parents are going shopping next week or next weekend at all, it might be useful for you to have one or more of the following, different flavours of crisps, or different flavours of jam, or different flavours of flavoured yoghurt. It's not essential, but it's just a little idea. So as I said, we're moving on to part 3 of this topic, which is esters. And I've got a little summary here, but really what we're going to be looking at with esters is quite similar to aldehydes and ketones. So we're going to look at their functional group, their naming and structures and things like that. And then we're also going to look at making esters and something called hydrolysis of esters. So esters are made in something known as condensation reactions. So we're going to learn what those are. And then we're also going to learn about hydrolysis reactions, which are used to break esters up. You've got more detailed learning outcomes on page 3 of the notes, but I'm not going to spend any time reading through those just now. So we're going to begin on page 29 of the notes, and the title here is Flavour Molecules Esters. So some esters are flavour molecules. It's not the only use or the only thing that esters are, but quite a number of flavour molecules are esters. Some esters are flavour molecules. So what we're going to focus on in this topic is we're just going to focus on the basics of esters structures, but then in the next topic, chemistry of cooking and cosmetic chemistry, we'll look in more detail at what specific how specific esters relate to different flavours. I think there is a little bit of that in this section as well, to be fair. And then hopefully when we're back in school, we'll be able to do the experiment where we make esters, and then you'll get to see for yourselves how we can take you'll get to smell them for yourselves, because esters, one thing that the SQ8 love you to know about esters is that they have a fruity smell. So let's start with that. A lot of the flavours and smells of certain fruits are due to ester molecules. So let's start with that key fact, because this is something that comes up pretty much all the time in questions, or at least I seem to think it does. So esters are compounds whose molecules contain the ester link, and we've got a structure here which shows the ester link. So I'm just going to circle the ester link in this structure here. So remember, R, I like to think of it as standing for the rest of the molecule. So R could be hydrogen or a carbonyl group, sorry, not a carbonyl group, or a hydrocarbon group, CH3, or a longer chain. In this particular structure, R1, so this R could be hydrogen or a hydrocarbon. R1 must be CH3 or a longer hydrocarbon chain. And the first thing I'd like you to think about is, in the diagram above, if R1, so this R was a hydrogen, what type of compound would it represent? So pause the video now and try and answer that question. Okay, and hopefully you've said carboxylic acid. So if that was a hydrogen, then we'd have the carboxyl group here instead of an ester link. Question 2, circle the ester link in the structure. Hopefully nice and simple. 2 seconds to do it. Okay, and hopefully you've circled what I have done on the diagram. So first thing to look at is how esters are formed, because that tells us quite a bit about the structure and how we get this ester link, and how the different halves of the structure around the ester link are related. So we're going to look at the formation of esters first of all. So esters are formed from the condensation reaction between alcohols and carboxylic acids. So we've learned about alcohols and carboxylic acids already, and an ester is always made of 1 part alcohol and 1 part carboxylic acid. We'll look at how that works in a sec. So in condensation reactions, 2 molecules are joined together with the elimination of a small molecule. The carboxylate group or ester link, so that's worth knowing. There's two different names for the ester link. I tend to use ester link, but it could also be called the carboxylate group. So the ester link is formed by the condensation of a hydroxyl group from an alcohol with a carboxyl group from a carboxylic acid. And this reaction links the two hydrocarbon chains together. So what you can see in this diagram here is that you've got your carboxylic acid with the carboxyl group, and we've got the hydroxyl group from the alcohol. We're not going to go into the details of the mechanism, but the way this reaction happens is that we combine the OH from the carboxyl group with just the H from the hydroxyl group to make water, and then this carbon here will join on to this oxygen here, and that's how we form the ester link. So the carbon with the double bond to the oxygen stays the same. Okay, so when we get our ester structure, this half, if we can almost draw a dotted line along the structure, this half, the half with the carbon with the double bond to the oxygen, has come from the carboxylic acid. Okay, so this part has come from the carboxylic acid, and the other half, the half where we've just got the oxygen with a single bond to what will probably be a carbon, that comes from the alcohol. So it's often very handy to be able to just draw a dotted line like this to split the ester up, and it'll help you when it comes to naming as well. Okay, so question 3 on this page says using full structural formulas, use full structural formulas to illustrate how ethanol and propanoic acid will react to form an ester. So I'm going to go through that with you, and I'm going to show you the moly mods as well. So we're starting off with ethanol. Ethanol, the ol ending tells us it's an alcohol containing the hydroxyl group, and propanoic acid, oic acid telling us it's got the carboxyl group. Eth means 2 carbons, so here's our ethanol here, and here's our propanoic acid, so prop with 3 carbons, so we've got the 3 carbons and then the carboxyl group here. So I'll pop these up here and then we'll draw the structures. Now, the way, something that's going to make this easier, actually, I've put these molecules side by side like this, but because it's the carboxyl group and the hydroxyl group that react, when you're drawing the formation of esters, actually it helps, it makes your life easier if you can draw the hydroxyl group and the carboxyl group facing each other. So we'll do that. Okay, so here are the structures here, and what's going to happen is, remember, the H from the hydroxyl group combined with the OH from the carboxyl group, these are going to combine to form water, and we're going to get a bond forming between this carbon here and the oxygen in the hydroxyl group. So we're removing the hydrogen and the OH to form water, so that's going to be one of our products. And then we're forming a bond between the carbon from the acid and the oxygen from the alcohol to form our ester link. There we go. So we'll just draw that in now. Okay, so we're forming our ester structure here. And remember again, we could draw a dotted line down the middle of this ester link, and this half comes from the alcohol, this half comes from the acid. We won't do that just now. We're going to look at naming on the next page, but I'll just give you the name of this one. So the alcohol used to make this ester here was called ethanol, so the name of this ester is going to start with ethyl, and the acid was propanoic acid, so the name's going to end with propanoate. That is 2 words. So this is an ester called ethyl propanoate, and we're producing water in this reaction as well. And something you might notice is that I've kind of deliberately drawn the ester link the other way around here. In your examples up here, you've got your carbon with the double bond oxygen on the left and the other oxygen on the right. It really doesn't make any difference. because as we know, these molecules can be flipped around. So the way I've drawn it is like this, but we could flip it over and we could have the carbon with a double bond to the oxygen on the left and the single oxygen on the right. So just to remember that there's different ways that we can flip these molecules over. Okay, so we're moving on to page 30 now. Page 30 is on naming esters, and then the second half looks at drawing the short and structural formula. Now, I think that you can probably do page 30 without much input from me, so I'd like you to pause the video now and read through page 30 and try and complete it yourselves. Just go with your gut, but I will show you the answers in a few seconds, just so you can check that you're going along the right lines. Okay, so here are the answers to the first half of page 30. And then here are the answers to the short and structural formulas. So really just how you would expect, to be honest. So notice you can recognise the ester link from the Q part in the middle of a formula, or ook. And you remember something that I made a wee mistake on here was accidentally writing CH2 for this carbon, but remember this carbon here doesn't have any hydrogen, so it's just OOC on its own and then a CH2 in this one here. Okay, so moving on to page 31, we're going to look at ester structures and names. If you're feeling quite confident, you can pause the video now and then just fast forward a bit and check that you've done the answers right. But I am going to go through I think at least the first couple of these, because I think it's not quite as straightforward as naming some other compounds, because you've got to figure out which half of the molecule is from the alcohol and which is from the acid. So we'll take this first one here. So for this first one here, we're given the full structural formula, and we can tell this is an ester because of the ester link here. So a carbon with double bond to an oxygen and then another oxygen here, but we've got hydrocarbon chains on both sides. So, like I mentioned when I first showed you the reaction to form esters, best thing to do is to draw a dotted line between the carbon with the double bond oxygen and the other oxygen in the ester link, and then the half with the carbon double bond oxygen, this half is going to be from the acid, and this half is going to be from the alcohol. Okay, so then we just have to count the carbons to come up with our name. So we're going to start with the alcohol because the first part of the name comes from the alcohol, and the alcohol half of this ester only has one carbon atom, and so the alcohol would have originally been methanol, and we're going to call the ester therefore methyl or methyl. Okay, and then the acid part, we've got 1, 2, 3, 4 carbon atoms, and therefore that would have come from butanoic acid, and so we're going to call the ester, thinking back to the previous page, we're going to call the ester butanoate. So we're going to call this ester here methyl butanoate. And then the short and structural formula, hopefully you're fairly confident with that. Okay, so again, just taking each carbon in turn is what I was doing there. So CH3, CH2, CH2, COO with no hydrogens, and then CH3 at the end. Okay, next one is propyl pentanoate. So this time we're going to work from the name. Propyl, the yl comes from the alcohol, and the pentanoate comes from the acid. So you can do this either way round really. I'm going to start with the alcohol side. So propyl, prop tells us how many carbons. Hopefully you're saying 3. So 1, 2, 3 carbons. And then remember the alcohol side, the carbon doesn't have the double bond to the oxygen. The carbon is just bonded to the single oxygen, or not the single oxygen, but the oxygen that's part of the chain, if you like, in the ester link. And then pentanoate, that's telling us there were 5 carbons in the acid. Pent means 5. So we're going to have 1, 2, 3, 4, 5. And the carbon, first carbon, if you like, in the chain of the acid is going to have the double bond to an oxygen here. So that's creating our ester link here. So the carbon with the double bond to the oxygen should be part of the acid side, which should have pent 5 carbons, 1, 2, 3, 4, 5. And then the oxygen, the sort of oxygen that's part of the chain of the ester molecule, is bonded to the alcohol side. It links the two sides, and the alcohol in this case is prop, so has 1, 2, 3 carbons. So we'll just add the hydrogens on. Okay, so I'm going to leave you to do the short and structural formula for that one. And to be honest, I think you'll probably manage with the rest of this page. So I've changed my mind, and the only other hint I'm going to do for you is the full structural formula for this one, and then I'm going to leave you to see if you can do the rest of the names and shorten structures yourselves and get you to submit this page for me to check. Okay, so there you go. When it comes to working from the short and structural formula back to the full structural formula, just remember that with the ester link, the carbon that doesn't have any hydrogens beside it, so there's no CH2 on this one, that must be the one with double bond to that oxygen there. Always worthwhile double checking you've counted your carbons right. So I've got my ester link here, and I've got 1, 2, 3 carbons on this side, and I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons on the other side. Okay, so make sure you finish off the rest of that, page 31. Okay, so moving on now to page 32, we're just going to have a quick look at the properties and uses of esters. So esters are used in flavourings, perfumes and solvents. Just mentioning that really briefly because we're going to look in more detail at their use in flavourings and perfumes later on. What we're going to do in this question 1 is we're just going to take a look at the intermolecular forces in esters, and we're going to look at them in comparison with a carboxylic acid. In this table we've got a ethyl ethanoate here, and we've got ethanoic acid here. Now if we count up the molecular formula for these, 1, 2, 3, we've both got, they're both a C4, O2, 2 oxygens, and then 3, 6, 8, 3 plus 2 is 5. Okay, so it took me a minute to count that there, but both of these should be, if I've done my counting right, C4O2H8 if we were just to look at the molecular formula alone. So what does that tell us? If they have the same number of each type of atom, how does that relate to intermolecular forces? What do you think I'm doing by counting these? Well, hopefully you're thinking, if they're isomers, if they've got the same number of each type of atom, that means that they must have the same number of electrons, and therefore similar strength of London dispersion forces. So these questions here, these questions are not going to be about LDFs because we're looking at comparison between esters and carboxylic acids, not in relation to London dispersion forces because they just relate to the number of electrons, but we're looking at the ester link and compared to the carboxyl group. So again, I'm not going to go through the answers to these with you, but the ester link is this functional group here, C double bond O, then we've got R on either side, and then our carboxyl group is C with a double bond O, O, H. So when you're answering these questions here, think about comparing the ester link to the carboxyl group when you're trying to figure out what type of intermolecular forces exist between molecules of ethyl ethanoate, which is the top one here, and a butanoic acid, which is the bottom one here. When you're answering these, I want you to try and focus this time not on necessarily a detailed explanation, but on just like a 1-sentence answer for these questions. So see what you can come up with for that. So first of all, looking at what the strongest type of intermolecular forces is between, first of all, the ester ethyl ethanoate, and then second of all between molecules of butanoic acid. Explaining why ethyl ethanoate is less soluble in water, and then explaining why butanoic acid has the higher boiling point. Like I say, try and focus on just 1-sentence answers for this. So if you want to pause the video, you can do that and answer the top of page 32. I'm just going to talk briefly about the next couple of pages. So formation of esters experiment. So this experiment would be to carry out a condensation reaction, but we're not going to look at that just now because it's a nice experiment. It's quite visual, as in there's quite a lot of little subtle things to look out for, which I think would be much better done actually in class. So we're going to skip the bottom of page 32. We're going to skip all of page 33, you will be pleased to know. And we are going to skip the top half of page 34. And this video, we're going to start again on the bottom of page 34. So pause now if you need to answer any of the other questions, otherwise keep listening, and we're going to finish off this little bit on esters. Okay, so the last little bit of this is hydrolyzing esters. So we saw previously that esters are made in condensation reactions between an alcohol and a carboxylic acid, so that's the joining together of two molecules. Hydrolysis is the splitting up of two molecules, and it's splitting using water. So esters react with water in hydrolysis reactions, producing the parent alcohol and carboxylic acid, and it's the reverse reaction to the formation of esters. So during hydrolysis, a molecule is split up using water, and that name, so lysis, you might remember this, I think we have discussed it before. Lysis means splitting, and hydro refers to water. So hydrolysis literally means water splitting. So we're using water to split up the ester to form the alcohol and carboxylic acid again. Question 1 here, it says draw the structural formula of ethyl ethanoate. I'll just run through that. So ethyl comes from the alcohol, and F tells us there are two carbons in the alcohol. So the alcohol is going to have that single oxygen that's part of the chain. Ethanoate tells us there are two carbons in the carboxylic acid half, so there are going to be two carbons here as well. Ethanoate, the carboxylic acid, is going to have the double bond to the oxygen here, and the ethyl, that's coming from ethanol, so we're just going to add in the hydrogens here. So again, if we split this in half along the line parallel to the carbon with a double bond to the oxygen, we would then have two halves, a half with the carbon with a double bond, which comes from the acid, and a half which comes from the alcohol. Both in this case have two carbon atoms. What does hydrolysis mean? I'm going to let you answer that. So on page 35, we then have the structural explanation for what's happening when the ester link breaks. So our ester link splits between the carbon with a double bond to the oxygen and the other oxygen, and then we add in water, just as it shows on the diagrams here. And that's how we regenerate the carboxylic acid and the alcohol. So really briefly, I'll just show you that with the molymods. So we've got our ethyl ethanoate, and we're going to break the ester link in the middle. We're going to add in water, but the water has to also split up into two parts. So our OH part of the water, one half of the water molecule will add on here to regenerate the carboxylic acid, which is this one here, and then the hydrogen, other hydrogen from the water, is going to add on here to regenerate our alcohol. So you have to write the above as a word equation and using shortened structural formulae. I'm hoping that you're able to do that, and I'm also hoping that you would manage this, so writing a structural equation and a word equation for the hydrolysis of this. So this is giving you the shortened structural formula, and the first thing for you to do with this one would be to write out the full structural formula for this before you write the word equation. Remember, in both of these, your word equations are always going to be ester plus water makes a alcohol plus carboxylic acid. You just need to give the specific names of the ester and acid and alcohol involved. So please just let me know via email or Teams if you've got any questions with those. I think you should be okay with it though. And then question 5, again, similar, just writing a word equation for the hydrolysis of octyl propanoate. So remember, that's the name of the ester, and you're just going to have ester plus water, and then you just need to name the alcohol and carboxylic acid that breaks up into. This may have been reasonably clear to you already, but just to highlight that condensation and hydrolysis reactions are both reversible reactions, so they can go in both directions and they can also happen at the same time. And that's why we use this two-way arrow here. So at any one time when we're trying to make our ester, we do have to do various things. We'll discuss when we do this in class a little bit about back to the equilibrium topic, about how we can favour the formation of the ester if we're wanting to make the ester, or how we might favour the breakdown of the ester if we want to split the ester back up into the carboxylic acid and alcohol. So question 6, does condensation refer to the forward or backwards reaction? I think you should be able to answer that. And then I also think you should be able to do this last page of this topic, which is a summary of the functional groups covered within the topic. So the only thing I'd like to say about this page, this bit here, is I want to just add a little bit in. So it says beside each functional group, write its name and the type of compounds it's found in. So remember, R can stand for any hydrocarbon group, or in some cases hydrogen. I want to also add in a little bit about intermolecular forces. So I'm going to leave you to find the names and the types of compound for the different functional groups. But what I'd like to highlight is that when we see an oxygen directly bonded to a hydrogen, that means that substances with this functional group can form hydrogen bonds with another molecule. Be really careful here. It's not that this is a hydrogen bond. The oxygen bonded to the hydrogen is joined by a covalent bond, so it's not that this is a hydrogen bond, but it means that substances with this functional group can form hydrogen bonds. I'm going to write hydrogen bonds there. Okay, equally here, this group here, we've got this oxygen bonded to a hydrogen, again, can form hydrogen bonds. But this isn't itself a hydrogen bond. Okay, when we look at these other two functional groups, on the other hand, we've got oxygens in here, yes, and we will have hydrogens probably if the R group has hydrogen, is a hydrocarbon section, but these molecules, because we don't have an oxygen directly bonded to hydrogen, molecules with these bottom two functional groups cannot form hydrogen bonds. However, because oxygen is significantly more electronegative than carbon, these two types of functional group do allow molecules to form permanent dipole to permanent dipole interactions. Okay. So you should recognise, as well as being able to tell the name of these functional groups and the types of compounds they're found in, you should be able to recognise the type of intermolecular force associated with each functional group as well. Okay, so as usual, this video has ended up a little bit longer than I hoped, but hopefully this week's work has taken a little bit less time. I'm going to set you a little Kahoot as well to complete just a little bit of revision of aldehydes and ketones from last week. Thank you very much for listening, and please remember to get in touch if you have any questions whatsoever. It's my job to answer them, and no question is a silly question.